If you're not able to hear me,
Yes.
just raise your hand or put your comments in the chat window. Well, very good. So let's get started. And see, today we are going to talk about linear regression as a machine learning technique. And just to get started, why linear regression? Most of the industry problems that or the projects that you see today, it's mostly 80% of the cases it is around linear regression. Why? Because the simplicity of this the statistical technique or this predictive modeling technique and the simplicity of explaining the results of this linear regression model. So you can say, hey, what's new in it? We can simply do like 2 lines of programming from Scikit-Learn or any kind of a Python library to get it done. That's not an issue at all. The idea here is how do we and where do I apply? Basically, finding out the application of linear regression in machine learning problems or connecting the real life business problems to a linear regression technique and finding out a solution and explaining that, that's a typical a challenging process. Constructing a business problem to or a statistical problem or a mathematical problem is the challenge today. Now, question could be why linear regression? Or why should we explain or why should we assume that the relationship between various variables in a data set of any problem could be linear? Because the linear relationship are the simplest and it's one of the non-trivial relationship that can be imagined, which is easy to work with, because the true relationship between the variables sometimes may not be linear but approximately linear. That's why it is easy to explain it to someone. And also, it is easy to understand, and we can correlate, we can associate the variables and understand their interpretations as well. Having said that, so let's look at a small use case and I'll explain. You can see my screen, right? If you are not able to see my screen, please let me know. Bikram, I'm not able to share my screen. Can you please give me the permission?
Just a minute. Actually, next to the video option, there will be share content.
Yeah, it is not enabled. The share content is not enabled. It's asking me system preferences. Yeah. Just let me know if you're able to see. No, it's still not enabled. I'm the host, no, right?
Just a minute.
Yep.
Just can you try now, sir?
Still not. Still, it is not. It's actually disabled. You can make me host. Maybe it will come. Okay, so till the time it is enabled, so let's talk about more. What is simple linear regression? What is multiple linear regression? So I understand. So when you try
You
to,
can try. Sorry, sorry.
I'm sorry.
You can try now.
No, it is not enabled.
I make you as a presenter. I
No,
guess
still it is not showing me as host.
not required host. Presenter, you can share the screen.
No, it is not happening. It's not happening. Hello.
Yeah, I can hear. May I know the error?
Sorry.
May I know the error? What sort of error you are getting? Because
It is not enabled at all. So like the legends that you see here, it has to be enabled, right? So this is share option is not enabled, and it's not clickable.
can you now? I made to host.
No, no, still it's not happening.
Just only you have to click on the share content because there is no such type of option like to allow you
That
to
option is
share the content.
no, the option is there, but it is not enabled. How do I share my screen?
If you if you click on the share screen, so one window will pop up. So from that you can share the either a tab or whatever.
No, I'm not sure how it's not happening. Not sure, Vikram.
Vikram, why don't you just present the slide? Ask him to forward you and you can just get it.
Definitely. Would you like to share me the your slide to me so that I can share the screen?
Yes, I can. Just a moment.
Should I draw the email ID to
Can you just put your email ID, please?
you? Yes. It's there on the chat.
Vikram, I have just shared one HTML page. Just open up that HTML page. Okay.
Yeah.
So,
Just
and it has the Python codes, etc. So people right now I can explain that. Okay.
just
Fine. So there are two kinds of linear regression technique, which is simple linear regression when you are looking at only one independent variable and one dependent variable. If you are looking at multiple independent variables with one dependent variable, that's called your multiple linear regression. So basically, this linear regression concept actually came from statistics, which is pretty clean and pretty powerful technique in statistics. It is being used, and in machine learning, the same technique can be used, right? So now, question here is whether it is predictive modeling or machine learning. The concept remains same. So it's a linear model. Why? Because the reason is that linear regression has around almost a history of 200 years. It has been studied from various possible angles, and that's why it's most powerful technique which can be used to predict the outcomes for any particular dependent variable. Okay, so linear regression, it has the dependent variable is also known as the explanatory. Hello, my voice is echoing, guys. Hello, Bikram, can you please put it on full screen mode? The screen is pretty small. Hello, Bikram. Hello, hello, hello. Hello, folks. Are you able to hear me? Hello, hello. Yes, Karti, you're able to hear me, right?
Yeah, it's
Uh,
audible. Go ahead.
Bikram, your screen is not visible, so I mean, it's not. I mean, the fonts are also
Yeah,
not
it's
visible. It's not.
yep, it's sort of blur coming up.
Uh-huh.
What you can do, I think you can check your internet connection, Vikram. I think the problem is from there only,
Right.
or even it's the resolution problem. I think maybe no, it's not that. Sorry.
So then, Bikram, can you just put your mic on mute? If there is some problem from your side, just put it on mute. Right, guys, meeting already started. Yeah, just facing some issues in terms of sharing the content. So we will get started and let them fix these issues when it comes up. So the idea here is how to apply linear regression in a business scenario or in a business use case, and how to interpret the result that is of most importance to us. There are different kinds of relationship that we can expect from a data set where the x variable, or which is considered as the independent variable, it is also known as predictor variable or explanatory variable. Predictors or the independent variables that explain certain relationship that is existing in a data set between the dependent variable and the independent variables. The dependent variable, which is also considered as the y variable, it's also known as response variable or outcome variable. Outcome means what we are expecting from the result. Okay. In any sort of business use case, we will try to correlate one x and one y and understand how it behaves. So linear regression is commonly used to quantify the relationship between two or more variables. It is also used to adjust for the confoundings, which means perfectly positive correlations. Part of our professional expertise, or when we are actually working on data science project, is to investigate the relationship between various variables to understand their relationship. Then we'll go ahead simply with linear regression and apply it, right? So linear regression basically quantifies the relationship between one or more predictor variables and an outcome variable or dependent variable, and it is commonly used for predictive analysis. We can predict what is likely to happen in future. Now, if I take very much like a most commonly or familiar relationship, that is sales and advertisement, right? So sales and advertisement, or sales can be associated with maybe price. Sales can be associated with maybe any other variables of choice. To understand the causal relationship that may exist, right? So let's consider that if I'm the let's take a owner of a business, I would like to sell my products. What are the considerations? So probably first consideration would be I will spend a lot on advertisement to bring my product to the notice of the customers. If my customers can see the product, they will definitely place orders. Now, my first problem would be to understand who are my customers and which channel they prefer. There are different channels: TV, advertisement, radio, newspaper, etc. Now, if you look at the current scenario, let's take the COVID scenario. Many people, they may not be looking at newspapers nowadays, right? Is it an effective way of making advertisement? That we don't know. But there are certain companies who are still continuing with the newspaper as a source of advertisement, right? So question here is, what is the most effective way of making advertisement? And if I advertise on this platform, how much revenue I'm going to get, right? So the regression analysis is typically used to make an assessment of all the channels and their effectiveness in terms of bringing ROI to the table. So this particular data set, the advertisement data that we are going to use in this linear regression analysis. So the advertisement data is basically, there is a sales column, if you look at in the data column, and there are three methods of making advertisement: TV, radio, and newspaper. So this data set is basically taken from Introduction to Statistical Learning. So that's a ISL as a book written by so this ISL book has certain data sets, and this is just a very small sample data set of 200 records, which is being taken from this particular book to understand the relationship. Now, if I'm a business and I know that most of my customers, they used to look at newspaper for like daily news requirements, and that was an effective way of making advertisement. And I was purchasing a space like a page or a second or maybe half page for advertisement. Nowadays, due to Corona, maybe people are not ordering newspapers. They have stopped asking newspapers. They are moved to online channels to look for advertisements. So is it an effective way of making advertisement? Probably no. If I have to increase my spend on radio or TV, could be more effective in increasing my sales, right? So linear regression is typically used to predict the sales if I make changes to my independent predictors. Now, to what extent I will my predictors, or if I change my spend on TV and radio by X percentage, what would be its impact on the one variable or the sales variable that is of utmost importance to me, right? Can you scroll down the page, please? So yeah, can you just scroll down further? So yeah, just hold on. Yeah. So the relationship between the sales and the newspaper, sales and the radio, sales and TV is important here. Now, is this linear? If it is not linear, then what kind of relationship it is? Is it polynomial? Is it any quadratic relationship? If I know the relationship, I can make predictions. So question here is, it's a function. So sales is basically a function of TV, radio, newspaper spends. The amount that you are seeing here, these are dollar values. If my sales is in hundred thousands, right, and I'm spending, let's take money on the TV, radio, and a newspaper, what should be the distribution? Should I spend 20% of my advertisement budget on newspaper? Should I spend 50% of my budget on TV? Should I spend like 30% of my budget on radio? What should be the distribution of my advertisement budget across all three different sources of making advertisement? So that's why you need to know the ROI, which is called the return on investment. How much I should put, where I should put, so that I will get maximum revenue or maximum sales from my advertisement efforts. So that's why we can use the linear regression concept. So basically, the linear regression model predicts the sales variable as a weighted sum of the feature inputs. The features are basically TV, radio, and newspaper. So the linearity of the relationship that makes the interpretation pretty easy. So linear regression models, traditionally used by statisticians, computer scientists, and other finance people also to take quantitative decisions or quantitative to solve quantitative problems. So linear regression can be expressed as an equation where y is a function of beta 0, which is called the intercept term, which means without any advertisement or without any spent on any sources of advertisement, we still should be able to make some sales, right? That's your intercept term. That is also known as the beta coefficient, beta 0. Then after that, other coefficients that you look at, you can say beta 1 times TV, beta 2 times radio, and beta 3 times newspaper, and plus the error term. So the predicted outcome of sales is a weighted sum of the features, the three features which are expressed as the betas, like beta 1, beta 2, beta 3, which represent the weights or the coefficients corresponding to each of the beta, corresponding to each of the advertisement sources. So the first weight, let's take beta 0, which is called the intercept term, and it's basically the like without any impact. If all other coefficients will become 0, still you will be able to make some cells. Like that's called your base cells, which you should be able to make, right? So if you scroll down here, so first of all, as a first step in regression analysis, we have to understand the associations, or first we have to look at the assumptions. What are the typical assumptions of a linear regression model? And why assumptions are required? So assumptions, because if the model is correct, right, then we can and how do we ensure that the model is correct? If all of the assumptions are met, all of the assumptions are satisfied, then we can assume that my model will work good, or my model will perform, or my model will hold true. So the model is the correct. If your model is correct, then your predictions are also correct. If your model is incorrect, your predictions are incorrect. And your model can only be correct when you meet certain assumptions. First assumption is linearity. The linear regression model basically forces the prediction to be a linear combination of features, which is both, you can say, its greatest strength and its greatest limitation as well. Strength in the sense, linearity leads to interpretable models. So you can easily interpret the effect of on the target column, and which is easy to quantify and describe it. And they're also additive. So it is easy to separate the effects, and you can understand what is the impact of one source versus multiple sources. So if you suspect the feature interactions or non-linear associations between features that could impact the target variable, which is sales, you can add more interaction terms and still use the regression concept here, right? The second assumption is about normality, which means it's assumed that the target outcome of the sales, given the features, follow a normal distribution. If this assumption is violated, then the estimated beta coefficients from the predictive models, right? The estimated coefficients or the confidence intervals of the features are quite invalid, right? Third assumption is about the homoscedasticity, which means the variance of the error term is assumed to be constant. The variance of the error term is assumed to be constant over the entire feature space. Suppose you want to predict the value of sales given that your advertisement spend is this much, your let's take a newspaper sale is this much, your radio, the spent on radio source as an advertisement is this much. So you can estimate a linear model that assumes this. Now, this assumption is really validated in practice, right? So homoscedasticity means constant variance. Your variance from the estimated error term should be constant over the feature space. And the next assumption here is independence, which means the features should be independent. That means it is assumed that each example or each instance is independent of other instance, right? So having looked at or looking at those kind of assumptions, the first step in building linear regression model is just a visual way or visual inspection of identifying the relationship. Then you can dig deeper to find out the mathematical concepts or mathematical associations. So first way is graphically. Let's look at. So the first column, this unnamed column, is not essential, not important. We can delete it, and we simply create a data frame. So using Python libraries, Python pandas library, you can read the data set. Once you read the data set, so those 4 columns you can retain, and you can go ahead with the further, right? I think I can see a question in the chat window. Let's look at this. Our model should have to be homoscedastic or heteroscedastic, right? See, homoscedastic, not a heteroscedastic. So it should be no heteroscedasticity, which means homoscedastic. Homoscedastic means constant variance, right? Homoscedastic means constant variance. Heteroscedastic means variance is changing. Variance is not constant. So your model should be homoscedastic. Okay, fine. Can you scroll down further, please? On this page. I think Kshitij, you are handling this, right? Yeah. Can you scroll down? So first thing here is, yeah. So once you scroll down, so here you can see what are the features. TV, advertisement dollars spent on TV for single product in a given market. Radio, advertisement dollars spent on radio. Newspaper, advertisement dollars spent on newspaper. And what is the response variable? The response variable is the sales variable. Okay. Now, if you scroll down further, so you'll find the associations are being represented in a scatter plot, and the y-axis. Kshitij, are you there? Can you please scroll down the page? Hello? Hello? Kshitij, are you there?
Just to be audible actually. Might be there will be some lag. Yeah.
Yeah. Can you? I think there is a huge lag, not even small lag. So with simple linear regression, when we have a single input, we can use the statistical or we can coefficients estimated from the model to predict the outcome. So which requires to calculate the outcome or the predictors. Now, there's a concept called ordinary least squares. So ordinary least squares is a procedure, or this or OLS procedures tries to minimize the sum of squared residuals, which means given a regression line expressed as a mathematical equation through the data, calculate the distance from each data point regression line and square it, and sum all the squared errors together, we can add it up. And this is the quantity that ordinary least squares seeks to minimize. And this OLS procedure treats the data as a matrix and uses the linear algebra operations to estimate the optimal values for those coefficients, which means all of the data must be available and you must have enough memory space to fit the data and perform the matrix operations in your computer. It is unusual to implement the OLS procedure, or which is called ordinary least squares procedure, yourself unless as an exercise in linear algebra, which means it is more likely that you will call a procedure in a linear algebra library, which is already integrated if you are using NumPy library, or if you are using Scikit-Learn library, the linear algebra concept is already integrated. Right. So if you scroll down further here, you can see the three graphs, the visual relationship between the features
Hey,
and
sorry for
responsibility.
interrupt. Sorry for.
The graphs should be represented, right? The graphs are not visible. Can you scroll down further? So there are three graphs you
Is
can
it good
see.
now? Is it
Yeah,
good
these
now?
three. So yeah, it is good now.
So
Okay.
actually, I have
So
some network problem on my side. So it would be great if there is something needed to scroll. You could just directly send me a chat. So that would be very for me too. Thank you so much.
okay, great. So yeah, so the next thing here is you can see the relationship. The y-axis shows sales, and the x-axis has radio and a newspaper. Sales and TV, you can see there is no strict linear relationship. It is a scattered relationship. It's like kind of a non-linear relationship where it's like you can't see a straight line representation of the dot points, right? And even sales and the radio, if you look at, it's all over scattered. There is no formal relationship between the two variables. And even you look at newspaper, it is further more scattered, which means there is no evidence of a clear linear relationship between the three variables. Now, in this case, is it wise to use, or is it appropriate to use linear regression? The answer is no, we should not apply linear regression. But is there any other technique that can be used here to predict the outcome sales? Probably no, right? The relationship could be non-linear, but if we change the variables, we could say TB square or TBQ, radio square, or log of radio, or newspaper square, or newspaper times radio, radio times newspaper, or radio times TV. So we could take interaction features between various variables over here, right? So first of all, will do a linear regression to understand the base accuracy, or can we get the base weights? When you apply linear regression, you will get certain weights associated with TV, radio, and the newspaper, right? So first we'll apply a baseline model, then we will look at how we can improve this model further by adding more features or more variables. Okay, so now the next thing is, what are the questions could be answered using this? So first question is, which source of making advertisement gives me more ROI, right? And what is the weight with it? How much revenue or how much sales I would be able to make if I alter my budgeting, or if I alter my spend on two different sources and I'll change the source. Suppose earlier I used to spend a lot on newspaper, but I know that newspaper has nothing to do with the sales predictions. So I'm spending a lot on newspaper advertisement. I will rather spend probably on TV or radio, right? There are two kinds of optimization techniques which can be used in linear regression to get the optimal value of the weights or the beta coefficients. So you could use the OLS, which is called ordinary least square procedure, or you could use something called a gradient descent. When there are one or more inputs, you can use the process of optimizing the values of the beta coefficients by iteratively minimizing the error of the model on your training data. Now hold on, please, hold on. So, no. Can you scroll up a little bit? Please scroll up a little bit. There are certain questions that need to be answered. Can you just scroll up, please? Yeah, stay on here. So the general questions you might want to get an answer is there a linear relationship between advertisements and sales? How strong is that relationship? Which ad types contribute to sales the most? What is the effect of each ad type on sales? ad spending in a particular market, can sales be predicted? So these are like 5 different sample questions that you could tell the business, right? So similar kind of questions you can extract, or similar kind of questions you can frame in the context of real practical business problems when you work on a data set. Okay, so you can scroll down further. So the simple linear regression here is basically functionally shown as beta 0 plus beta 1 x. Beta 1 is the coefficient for each x variable. So if you have 3 independent variables, you can just say beta 1, beta 2, and beta 3. However, beta 0 is called your intercept term, or it alpha in statistics, right? Now the objective is to estimate the model coefficients, which are called the learning parameters. And this procedure, or the iterative way of learning from data to find the coefficients, can be achieved by using a concept called gradient descent. Now, gradient descent is typically used in machine learning way of implementing linear regression. Now, this gradient descent works by starting with a random value for each of the coefficients. The sum of the squared errors are calculated for each pair of the input and output values. A learning rate is typically used as a scaling factor, and the coefficients are typically updated after each iteration in the direction towards minimizing the error. So the process is repeated until the sum of the squared error is achieved or no further improvement is possible, right? Now this graph explains the concept of an ordinary least square method, where the data points are represented as the red dots and the equation is represented as the blue line. The green lines are the errors, that is the difference between the estimated line and the actual data points. Now you will compute the differences, square the differences, sum it up, right? So that's called your ordinary least square method. So the gradient descent can be used to finding out the optimal values of the beta coefficients. When so basically a learning rate is playing an important role here to identify the optimal values of the beta coefficients. So it is known as a scaling factor, and the process is repeated until the minimum sum of square error is achieved. So when using this gradient descent method, you must select a learning rate, which is also known as alpha, that determines the size of improvement step to take on each iteration of the procedure. So a gradient descent is used, or is typically taught using a linear regression model, because it is relatively straightforward to understand that our data always keeps on increasing, and as my data changes, my coefficients should also learn from new data. So it is useful when you have a very large data set in the number of rows or in the number of columns that you may want to fit it to your computer memory, right? So gradient descent is a very, very powerful technique which is used to get the optimal value of the beta coefficients. Okay, you can scroll down further. Okay, fine. So next, we are going to look at the library that could be used. So Scikit-Learn is the library that could be used to create a linear regression model. And here, the data need to be vectorized as a metric so that linear algebra calculations can be done. So you can create x and y variables. Here, x variable are the feature columns, y is the target column. Now we can use this scikit-learn library, which is called like you can use sklearn.linear model, import linear regression, and you can initialize the linear regression, store it as an object. Then you can do object.fit x and y. Then you can directly print the intercept term and the coefficients from it. Now, once the coefficient is ready, suppose in this case you can see your mic is fine. Guys, can you please put your mic on mute?
मतलब बस ग्राफिक
Hello.
नहीं मतलब मुझे तो ग्राफ ही दिखाई दे रहे थे, बस मुझे इतना पता चल रहा था ग्राफ है ये, इतना तो पता चल गया था मुझे। मैथ का
Can you
ग्राफ आ
mute
गया,
yourself?
मुझे क्या हुआ तुम्हारा अब तक मैंने अभी तक चला रखा, मैंने कहा हम्म, चलिए हो गया। ठीक है, सो चलिए होगा।
Yeah, sorry for the interruption, guys. Yeah, Pradeep, you can continue.
Okay. So first we took TV as the independent predictor and the Y as cells as the target column. So here we can look at Y equal to beta 0 plus beta 1 times X. Y the dependent variable is a function of intercept term, which is 7.03, and the beta coefficient value is 0.04. Then once you have this equation established, then you can make a prediction. Suppose here next you can say, hey, if I am going to spend $50 on TV, what would be my expected sales? So you can use this equation to make a prediction. Now, once you use the model to make predictions, you can do that for the entire data set as well. Now you can generate the predictions for the entire column or entire data set. For each record, you can generate predictions, and you can represent the actuals and predicted values in one graph format to look at how the regression line fits to the data. So if you look at line number 14, the code line number 14, you can see a graph over there. So the sales and the TV are being represented as two axes, and there is a red straight line which is connecting or which is shown as the equation, right? Now, how good this model is. So is linear regression having high bias or low variance model? Or is it like low bias and high variance model, right? So it's a high bias and low variance model. Why? Because under repeated sampling, the line will stay roughly the same place, which is low variance. But the average of the models, of those models who won't do a great job capturing the true relationship, which is called high bias. Now, low variance is a useful characteristic when you don't have a lot of training data. However, a closely related concept is called confidence intervals. So statistical models that calculates 95 interval of your model coefficients, which are typically interpreted as if the population from which the sample was drawn was sampled 100 times, approximately 95% of the confidence intervals would contain the true model coefficient, right? So you could use the scikit-learn library for computing the linear regression. You could also use the START models. There is an alternate library which is called statistical models or START models API in Python also to compute the linear regression. Start models is a statistical way of representing or statistical way of computing the model. Scikit-learn is a machine learning way of computing the model. Now, keeping those in mind, will only have single sample of data, not the entire population of the data. So the true coefficient is either within the interval or it is not. But there is no way to actually know this. So we estimate the coefficient with the data we do have, right? So we show uncertainty about the estimate by giving a range that is the coefficient is probably within this. So once we compute the coefficients and their confidence, then the next process is about testing the hypothesis and understand the p-values to estimate whether the coefficient is the estimated coefficient is within this 95% confidence interval or it is outside of this confidence interval. So the closely related concept here is hypothesis testing. And what hypothesis we are going to test? We are going to test that there is no relationship between TV and cells, which is represented by beta equal to 0. If coefficient value is 0, which means TV and cells, they are not associated at all. And the alternative hypothesis is there can be a relationship between TV ads and cells. So how do we test this hypothesis? The objective here is to reject the null hypothesis. If we reject the null hypothesis, then the 95% confidence interval does not include 0. And this is represented by the p-value. So p-value represents the probability that the coefficient is actually 0. And if the probability is the p-value is less than 0.05, you will assume that your you will reject the null hypothesis and you will assume that your beta coefficient is not actually 0. It is different from 0. So if the 95% confidence interval includes 0, the p-value for that coefficient will be greater than 0.5. So If the 95% confidence interval does not include 0, the p-value would be less than 0.05. Hence, a p-value less than 0.5 is one way to decide whether the relationship between the feature and the target column is making sense or not. So the p-value for television spent is, you can see here, as far less than 0.05. So we believe that there is a relationship between TV ads and sales, but to what extent or how good it is, we don't know. So we need to figure out how good my model is. The most common way to evaluate the overall fitness of a linear regression model is looking at the R-square value or adjusted R-square value. If we compare both in case of a single explanatory variable or in case of a one independent variable regression model, yeah, in case of a one independent variable, you can look at R-square. However, when you have multiple independent variables, you should look at adjusted R-square values, right? So in this case, R-square is 0.61, right? Is that a good value? Is that not acceptable? Right? So R-square greater than 0.8 is expected, which means 80% or more than that is considered to be a good model. If R-square is less than 80%, then probably there is a scope to increase the model accuracy. Probably there is a scope to improve the model, right? Either by adding more features or transforming certain features, right? So now, since first we are getting 61% as R-square value, now next is we'll go for multiple linear regression model by adding more independent features. Now, radio and a newspaper, we are adding as additional features. Our feature column now will get extended to 3 features: TV, radio, and a newspaper spends. Y variable remains the same. We'll be using probably the same API, linear regression API here to fit the linear regression coefficients. And when we fit the model once again, I can see my intercept term now reduces to 2.93. My predictors have coefficients for TV 0.04, the radio it is 0.18, and for newspaper it is negative 0.001. So how do we interpret these coefficients? So we can interpret this way, like for a given amount of a radio and a newspaper ad spending, an increase of $1,000 in TV ad spending is associated with an increase in sales of 45.765 units, right? So we can use the even start model also you can use. So start model, when you are using and printing the summary of it, you can find the R-square and adjusted R-square. Since it is a multiple linear regression model, it makes sense to look at the adjusted R-square values. Why? Because the difference between R-square and adjusted R-square is a function of a number of independent features that you have added. If features are meaningful, you will find hardly any difference between R-square and adjusted R-square. If features are not meaningful, which means redundant features you have added to the data, then you will find significant differences between R-square and adjusted R-square. So always the adjusted R-square is considered as the measurement of goodness of fit of a linear regression model. And ideally, you should look at adjusted R-square, which is more than 80%. Now, in this example, if you look at TV, radio, newspaper, all three are features, and sales is the target column. Your adjusted R-square value is now 89.6%. So, which is a pretty good model. Now, once we have the adjusted R-square, which is acceptable, then we'll go back to the coefficients and their corresponding p-values. So, coefficient value for TV is 0.04, for radio it's 0.18, and for newspaper it is negative 0.0010. Now, if I look at the probability values or the p-values and their confidence interval values as well, right? So, p-value for intercept, TV, radio, all three less than 0.01, which means they are statistically significant. However, one predictor value, which is the newspaper coefficient, which is minus 0.0010, it's not statistically significant because the p-value is greater than 0.05. Hence, will not be able to reject the null hypothesis over here. And if you are not rejecting the null hypothesis, which means it is the beta coefficient is equal to 0. That means it is not within the confidence band or the confidence interval band, right? So what are the key findings we learn from this output? We learn from this output that TV and radio have significant p-values, whereas newspaper doesn't have. Thus, we can reject the null hypothesis for TV and radio, and there is no association between those features and sales, and fail to reject the null hypothesis for newspaper, which means TV and radio ad spending are both positively associated with sales, whereas newspaper ad spending is slightly negatively associated with sales. However, this is irrelevant since we have failed to reject the null hypothesis for newspaper. So, the interpretation of newspaper as an ad spending source we cannot consider because we are failed to reject the null hypothesis. However, the TV and the radio ad spending are positively associated with sales, and this has already been verified by the p-values. So this model has higher R square, which is 89.7%, and adjusted R square is also 89.6%. So the difference is very minimal between R square and adjusted R square. Now next process, here it is a robust model because all the available features that we have, we are using it to make predictions. Next step is feature selection. How do I decide what features to be included in my final model? We could try different models. Only keep the predictors in the model if the p-values are less than 0.05. And check whether the R-square value goes up when you add new predictors or not. And what are the drawbacks of this approach? The linear models quite upon a lot of assumptions, R-square, p-values, etc., etc. So using a p-value cutoff of 0.05 means if you add 100 predictors to a model that are like pure noise, 5 of them will still be counted as significant, which means R square is also prone to overfitting. So there is no guarantee that a model with a high R square value would generalize well. Now that's why R square will always increase as you add more and more redundant features to the model, even if they are unrelated to the response variable. And your adjusted R square actually penalizes for the model complexity, and adjusted R square is the right way to look at. Now here we could do some feature transformation. So what we can do, we could look at let's take the probably maybe the number of advertisements, or looking at the advertisement source, we could add a new variable which is called a small size advertisement, large size advertisement, medium size advertisement by looking at the value. If on TV, let's take I'm giving like 30-second advertisement versus 7-second advertisement, both will have two different kinds of impact. The impact will not be similar. Similarly, full page newspaper advertisement will have different kind of impact versus a quarter page advertisement space, right? So if I add another categorical variable here, which is considered as size of the advertisement, like small, medium, large, and we could say if this impacts the sales variable or not, definitely it impacts. Now, how good the model will be, or something like, let's take you are doing like newspaper advertisement. If the area is rural area or urban area or remote area, that also matters, right? So it is also a function of product availability and outlook of people, etc., etc. So if we add more features into the model by using like rural, urban, suburban, size of advertisement, etc., as more features, we could dummy variables to the model. So we could add more dummy variables to the model to make predictions, and we could see improvement in the model result as well. And finally, once we create the model, next process is just to evaluate the assumptions, whether the assumptions hold true or not. If it is not holding true, then we have to apply some transformations and we have to evaluate whether the model is good or not. So first is linear relationship. Of course, that is already verified by looking at the scatter plot. Initially, when we look at the scatter plot matplotlib function. And next is multivariate normality. So probably from the final regression model, you can extract the error value and plot it and see if it is following a normal distribution or not, right? So Is linear regression the sample size rule of thumb? Is that in case of a linear regression, at least you need 20 cases per independent variable in the data. So here we have 200 data points. Now if we are adding only 3 features, so 60 data point at least is required, and we have 200 data points, which is quite good. However, the more data that you have, that will make the calculation better, or the model would be generalizing to unknown data as well. Primarily, the linear regression needs the relationship between independent and dependent variables to be linear. If it is not linear, then you could do transformation of the features. You could add it as dummy variables into the data, right? Now, linear regression analysis also requires all variables to be multivariate normal, which means once you create a quantile plot or normality plot, you can do a test, or you can do a statistical test, which is called KS statistical test, to understand whether the data follows a normal distribution or not, right? And also you can look at multicollinearity. Multicollinearity could be or can be explained as the high correlation between independent variables, right? If there is a very high correlation between in all the independent variables, then that's called multicollinearity. And the acceptable limit of multicollinearity is for small data sets, it could be 10. For any predictor, if the multicollinearity value is more than 10, and how it is measured? It is measured through a factor which is called variance inflation factor. It's called VIF. The VIF value, if it is greater than 10 for any predictor, you have to drop that predictor, or you have to identify any alternate way of introducing that variable to the data, right? If multicollinearity is found in the data, centering the data could be like a mean normalization or standardization could help you, right? However, the simplest way, I mean, if after doing normalization, it is not removing the multicollinearity is not getting removed, you should consider deleting that particular variable from the data, which means it has high correlation with any other predictor as well, right? Autocorrelation is also considered as autocorrelation. So ideally, no autocorrelation should be there. No autocorrelation could be your error should not be a function, or error should not be represented as a function, which means you could use another equation to predict the errors. That should not be the case. And the last assumption is that homoscedasticity, which means equal variance, right? So to test it out, it is called Goldfeld and Quant test. It's a mathematical state test which could be used to identify whether the data is heteroscedastic or not. If homoscedasticity is present, you could do a nonlinear correlation matrix, or maybe you can do some transformations like logarithmic transformations or polynomial transformations of your input features to make it robust or make it work, right? So yeah, so that's all. If you have any questions, you can ask me now.
Thank you, Pradeep. So actually, students have asked few of the questions. So just I wanted to have a look on that. Just a minute.
Yeah, I can see. Please share the content. Running, yes, the content can be shared. Please share this HTML page. It's a Jupyter notebook which is written as a HTML page. You can take it. Okay.
And one more question is /DNN for making a control signal for any device like prosthetic control. Can we implement it in mathematical form that can run on Arduino or Raspberry Pi? I'm putting this question.
Sorry. Let me check the question here. Okay. Yeah, I can see. Yeah, we have to check linearity, independent, normality, and equally reliable and homoscedasticity. Yeah, that is correct. How to use ML DNN for making a control signal of any device like prosthetic control. Can we implement it in mathematical form that can run on Arduino or Raspberry Pi? You can do that, Karthik. Yeah. So you have to define this problem. Now, when you say control signal of any device, it's not exactly ML model. It's a reinforcement learning. Why? Because if your system is taking a wrong signal or wrong path, you have to penalize that path. And if it is taking a correct path, you have to provide a feedback, which is a good feedback, a positive feedback, right? So to design such a system, you have to, of course, a mathematical form you can express, but it's not a DNA or ML. So it's a reinforcement learning problem. Hope I have answered your question, Karthik. Yeah, any other questions? Normality and linearity, yes. Normality, linearity as in like if you put X and Y, like cells and TV, it should form a straight line or the dot points should be forming a line, right? Instead of, even if it's not strictly a straight line, it should be like a different dot points, but it should form a normal or linear pattern, a straight line pattern. However, in this data example that we saw, it is scattered all over the place. It's not forming a linearity here. Normality means your error terms or your when you do actual minus predicted, the errors that you compute, it should be normally distributed. If your error is not distributed normally, which means having a very skew value on the left hand side or on the right hand side, which means there is some degree of skewness, right? That's how you will get the concept of normality and linearity. Normality, you can do a case test, and linearity, you can look at maybe correlation values to identify linearity, which is a good source for machine learning. Yes. So I would recommend Google's machine learning course. Google has open source machine learning course. You can pursue that. How to find correlation between variables? Yeah. So yeah, there are three kinds of correlation. If your data is continuous, you should go for Pearson's correlation coefficient. If your data is binary, then Kendall's correlation. If your data is ranking, like 1 to 10 rank or 1 to 50 or 1 to 100 rank, then you could go for Spearman's rank correlation coefficient. And of course, there are different libraries to use. You could use Pandas library, Scikit-Learn library, start models, find the correlations between variables. Mathematically, you can compute the correlations, and graphically also you can represent the correlations to understand the associations. What is the what is the test used for checking equally reliable? What is equally reliable? Can you please elaborate a little bit? Do we need to check assumption before and after applying linear regression model? Yeah. So once you finalize a linear regression model, then you should check the assumptions. Your first objective is to get a good model. Now, once you get a good model, then you can evaluate whether the assumptions are satisfied or not. Okay. Let us say if there is a column age and if there are any categorical data, then it will be a problem. Right. So yes, yes. So in that case, you could, yes. In that case, you could use maybe independent, if your categorical data is independent, right? And you want to understand the association, whether, is it like you were saying, if my category, let's take married, unmarried, and age is a column, right? And you want to understand the association between that. So, or maybe you can say the variance or the changes, or maybe the average between married versus unmarried. If that's the case, then you could use a t-test, a statistical test to understand if there is a difference or not. How can we fine tune the parameters of a linear? Yeah, so literally the linear regression doesn't have enough parameters to fine tune. If you are using a gradient descent, you could fine tune maybe probably the alpha, which is the learning rate, or you could do changes to the regularization parameter, which is L1 for lasso and L2 for reach. Those regularized parameters you could alter to find out or fine tune the best model, because it's a simple linear regression is a very simple model. It doesn't have much hyper parameters to fine tune the model. Any other questions?
Yes.
Relation between logistic regression. Okay, so in case of a logistic regression, your target column has binary values, which is 0, 1, or yes, no, true, false, accept, reject, fraud, no fraud, cancer, no cancer. So when you have two discrete values in the target column, you could use logistic regression. If your target column or dependent variable is continuous, like sales, revenue, profit, then you could use linear regression. In age columns, there will be numbers, but let us say due to some problem, there are letters like that. Yeah, that's a data cleanup issue. So you have to clean up the data. If your column is numeric and there are some characters or letters, then you have to clean it up. How can we find that? You could do simply describe function. In pandas library, if you apply it on the data, simply put a describe function. Once you put a describe, if the numeric column has categorical values, your mean, median, and any kind of a descriptive function will not work there. Then you will get to know that probably there is some error, right? Overfitting and underfitting can also occur in linear regression. Yes, that could happen. Yes. How to handle that? Yes, definitely you have to do a trend test validation. So you need to have first like a large data set. Split the data into train, test, validation. Train the model, test the model, then again validate on another sample. If there is no difference between test and validation, then model is right fit. If huge difference is there, then probably underfitting or overfitting. In that case, you have to probably resample the data or get more records. Which is the best option to fill missing values, mean, median, mode, or any other factor? It depends on the situation. If your data is already skewed, then you should go for median best imputation. If your data is normally distributed, you should go for mean imputation. If your data is like maybe mode cannot be used as a imputation technique, kind of numeric factors. K-fold cross-validation can be applied. Yes, K-fold cross-validation is to, yeah, so that can be applied to avoid the overfitting. That's why I said like a resampling you have to do. Do a resampling, do a trend test validation, and look at the variations in the accuracy. If it is consistent, then it is fine. If not consistent, then probably you have to maybe change the model. Any other questions?
So I guess we are done actually. Thank you everyone for the entire participant. And if all of you like participant, if you wanted to get in touch with the Pradeep sir, so you can connect with the LinkedIn, and maybe in the future if you're having some sort of questions, you can ask over there. And yeah, thank you everyone.
Sure,
We
yeah.
are great to, and yeah, we are great for the time and effort you took to share your thoughts and experiences. And thank you very much, sir.
Yeah.
It was a great and wonderful session.
Yeah, welcome everyone, and yeah, stay connected. If you have any questions, please put it in maybe LinkedIn. I'll answer your questions. Yeah, LinkedIn. Yeah. You can share the notebook, Vikram, with all the folks.
Sure, definitely. I'll do that.
Sure. Okay. Thank you. Thanks everyone. Bye bye.
Bye. Thank you everyone again.